In this video, we're just going to go over a couple of other examples with separable differential equations, and then we're going to look at an AP problem. Okay, so here what we want to do is find the general solution to the differential equation, and then we want to find the particular solution using the initial condition. So in this example, we have xy prime equals y. So first off, we're going to use that information to find the general solution, and then we have y of 2 equals 2, and we'll use that initial condition to find our particular solution. So we want to remember that y prime is the same thing as dy over dx. So this would really be like x dy over dx equals y. So from here, we need to separate the variables because we want to get the y's on the same side and the x's on the same side. So I'm going to kind of switch everything around here. So I'm going to first divide both sides by x. So I get dy over dx equals y over x. And then from here, I will divide both sides by y and multiply both sides by dx. So this is very similar to what we did the last time. So I'm going to get 1 over y dy equals 1 over x dx. From here, I can take the integral of both sides. So I'm going to take the integral, take the integral. So the integral of 1 over y dy is going to be ln absolute value of y. Integral of 1 over x dx is going to be ln absolute value of x plus c. Okay, from here, we want to get y by itself, so we need to change forms. So I know that the base of my ln is e, so I'm going to say e to the ln absolute value of x plus c equals absolute value of y. And remember, when we have something that's being added in the exponent, I can rewrite it as different bases, or the same base, sorry, but being multiplied together, because multiplying the exponents when you have the bases the same is really adding the exponents. So I'm going to rewrite this as e to the ln absolute value of x times e to the c, and that's equal to the absolute value of y. All right, so when I multiply these together, I can add add the exponents together. So what we're going to do here, we know that e to the c is just a constant, so that's really just c. And when I have e to the ln, absolute value of x, e to the ln of whatever is going to be whatever, because the e to the ln are going to cancel each other out. So what I end up with here is going to be, I can drop the absolute value bars on the y, so I'll say that y is equal to the constant c, and then these will cancel out, and I'll be just left with the absolute value of x. So this is my general solution. So now I want to find the particular solution using the point that they gave us. So they're telling us y of 2 is equal to 2. So that means we're using the point 2, 2. So at 2, 2, we're going to plug in our information into here. So we'll say 2 is y, c is going to be c, absolute value of x, which is 2. So we get 2 equals 2c, so c is just equal to 1. So our particular solution will just be y equals the absolute value of x. Okay, let's look at another example here. All right, so this one looks a little bit complicated because there's a lot going on here. So we have to, again, find the general solution, then use the initial condition to find the particular solution. So I need to get the y's on the same side. Well, we have a little bit of an issue. I can't just subtract this 2y because I have another y here, but this y is attached to the x. So when we have something like this, we want to think about, could we maybe factor? And yes, we can. So dy over dx, we're going to leave alone for now. So if I look at this expression here, I can group it. So if I group the first two and I group the second two, I'm looking for greatest common factors. So I'm going to pull out a y. So now I have x plus 2. And then here I'm going to pull out a 5, and I have x plus 2. So this will be dy over dx equals y plus 5, x plus 2. So from here now, we can separate the variables. So I'm going to divide both sides by y plus 5, and then I will multiply both sides by dx. So I'm going to get 1 over y plus 5 dy equals x plus 2 dx. Okay, so from here, again, take the antiderivative, so integral of both sides. The integral of 1 over y plus 5 dy, that's going to be ln, absolute value of y plus 5. On the right-hand side, we're going to get 1/2 x squared plus 2x, and then plus c. So again, similar to the previous problem, we need to get the y by itself. So we are going to have to change this to an exponential. So the base on the ln is e. So we'll say e to the 1/2 x squared plus 2x plus c is equal to the absolute value of y plus 5. Okay, so similar to how we did the last problem, because we have this plus c that's being added into the exponent here, we could rewrite this, and I'll write this down here, as e to the 1/2 x squared plus 2x times e to the c equals absolute value of y plus 5. Remember, this e to the c is really just c. So let me bring it over here. So we'll say that we've got c e to the 1/2 x squared plus 2x, and that's going to be equal to y plus 5. I'm going to drop those absolute value bars now, right, because we know that it has to be positive if it's the ln of something, so it always needs to be positive. And now we can subtract 5. So we can get our general solution of y equals ce to the 1/2 x squared plus 2x minus 5. So this would be our general solution. But now we want to find the particular solution, and that's going to be based off of the initial condition they're giving us, which is y of 0 equals -1. So we're using the point 0, -1. So we're going to plug that in. -1 will be our y. Okay, c e to the, if I plug in 0 for x, I'm going to get just an overall 0 up there, minus 5. So I can add 5. So I'll end up with 4 equals, and e to the 0 is going to be 1. So c times 1 is c. So I get that c is equal to 4. So my particular solution would be y equals 4e, to the 1/2 x squared plus 2x minus 5. Okay. And then lastly, we're going to look at an AP problem, kind of putting this all together and reviewing linear approximations, which was also called linearization, that we did a while ago, but hopefully we'll remember. So here's an AP problem. We're given a differential equation, dy over dx equals -2x over y. So on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. So I'm just going to go ahead and just fill this in real quick. So I can tell that when my when x is equal to 0, the entire slope is going to be 0. So I can make my horizontal lines. And notice that the x-axis doesn't have any dots on it. That's where it would be undefined. Oops, so pretend that those are straight. And then I'm just going to fill in the rest here. So this is just basically going to look like this. So when they grade questions like this, they're just looking to make sure that all of the 0 slopes are correct. And that's usually what it's easy enough to figure out. It's whatever's going to make it 0. And then for the other ones, they're just looking that they're the right sign. So whether they're positive or negative, not necessarily the steepness of the line. So here's our slope field. Part B, let y equals f of x be the particular solution to the differential equation with the initial condition f of 1 equals -1. Write an equation for the line tangent to the graph of f at 1, -1, and use it to approximate f of 1.1. So we did questions like this a while ago. Okay? Basically, all we're trying to do is find an equation for a line. We need to find the slope. We have a point. We know the point is 1, -1. So we have to find the slope of the line, but good thing that they gave us dy over dx, because that's the slope. So all we're going to do is plug in 1, -1 into our function. So let's write this over here. So dy over dx is equal to, I'm going to plug in 1, -1. So I have -2 times x, which is 1, divided by y, which is -1. So I end up with -2 over -1. So I end up with 2. So that is my slope. Once I know my slope, I can write the equation of the line. So I'll say y equals, not y equals, I need to equal, by equals, oops, too big of an eraser. Sorry, point slope form. So y minus the y, so since it's -1, we'll get +1 equals the slope of 2 times x minus the x value. So we could leave this as our answer if we want to go ahead and figure it out. This would be y equals 2x, and then this would be -2 minus 1, so -3. Okay, so this would be, write the equation, great. Use it to approximate f of 1.1, so that means that I have to then figure out what the answer would be when x is 1.1. So f of 1.1 would be 2 times 1.1 minus 3, and that would equal -0.8. So all we're doing here was just actually finding the equation of the line by using the differential equation to find the slope, and then we just plug the point in to approximate it. And then the last question is what we were just working on, find the particular solution. So whenever they ask for the particular solution, that means use separation of variables and find the antiderivative of it and solve for y. And they're giving us this initial condition. So I'm going to use this, and I'll just rewrite it here. So dy over dx equals -2x over y. So to separate the variables, I'm going to multiply both sides by y, multiply both sides by dx. So I'll get y dy equals -2x dx. Okay, from here, we are going to take the antiderivative by taking the integral. So we're going to end up with 1/2 y squared equals -x squared plus c. And then I'm going to multiply both sides by 2. So I'll get y squared equals -2x squared plus c. So I'm going to keep c as c because even though I multiply it by 2, I'm going to still just get a constant. So now I'm going to take the square root of each side. So y equals, remember when you take the square root, you get plus or minus the square root of -2x squared plus c. So that is our general solution, but we need to find the particular solution with the given initial condition. So here we will use 1, -1 as our point. So we're going to plug in -1 for y. Now, since we have that plus or minus with the square root, we have to figure out, are we using the positive square root or the negative square root? And it's dependent on where the point is. So the point 1, -1 is going to be in the fourth quadrant, meaning that our square root would have to be negative there. So we're going to use the negative version of the square root of -2x squared plus c. And now we're trying to solve, oops, sorry, not x. It would be 1 for x. So we would have, oops, 1 squared. So we end up with -1 equals negative square root of negative 2 plus c, because we squared that one. So now we're going to square both sides. Yeah, I'll change colors. Why not? So I'm going to square this side and square this side. So negative 1 squared is just 1. When I square this negative, it becomes positive. When I square the square root, it goes away. So I have negative 2 plus c. So I end up getting that c is equal to 3. So since c is equal to 3, we're just going to plug that in where our c is, and we're going to end up with our particular solution, which is going to be y equals. We're using the negative because it's for that point that's in the fourth quadrant. So negative square root of negative 2x squared plus c, and c we know is 3, so plus 3. And then this would be our, particular solution.